Radius equals radius plus 1. In algebra, subtract radius from both sides and you get 0 equals 1, a contradiction. In Python, this line runs perfectly. Understanding why reveals how Python stores values in memory, attaches names to them, and evaluates expressions. Three ideas drive everything here: objects, variables, and expressions. Every value in Python is an object, and every object has a type. The number 3.14 is an object of type float. The number 20 is an object of type int. The type matters because it tells Python which operations are valid on that object. You can multiply two floats. You can raise an int to a power. Operations that make no sense for a type are rejected. So when Python sees a value, it always knows two things: what the value is and what kind of object holds it. Assignment binds a name to an object in memory. Take two lines. Pi is set to 3.14. Radius is set to 2.2. Track this with a memory diagram. The first line creates a float object holding 3.14 somewhere in memory, then attaches the name pi to it. The second line creates another float object holding 2.2 and attaches the name radius. The name is not the value. The name is a label pointing at an object. This distinction between names and objects explains everything that follows. Expressions combine objects with operators. Area is set to pi times radius to the power of 2. Python evaluates the right-hand side first. It looks up the name pi and retrieves 3.14. It looks up radius and retrieves 2.2. Then it applies operators by precedence, exponentiation before multiplication. 2.2 squared is 4.84. 3.14 times 4.84 is 15.1976. That result is a brand new float object created in memory. Only then does Python bind the name area to it. Every expression follows this pattern: retrieve, substitute, compute, create a new object, bind the name. Now the puzzle from the start. Radius is set to radius plus 1. The right-hand side evaluates first. That rule resolves the paradox. Python looks up the current value of radius, which is 2.2. It adds 1, producing 3.2. It creates a new float object in memory holding 3.2. Then it rebinds the name radius. The arrow moves from the old object to the new one. The equal sign here is not mathematical equality. It is an instruction. Compute the right side, then attach the name on the left. Read it as becomes, not equals. Radius becomes its old value plus 1. No contradiction. A common misconception. People picture the 2.2 changing into 3.2 inside its box. That never happened. The original object 2.2 was not modified. Python created a separate object and moved the name to it. The old object still sits in memory, now with nothing pointing at it. This distinction, creating new objects versus modifying existing ones, is central to Python. Numbers can never be modified in place. Later, with lists and other structures, some objects can change in place, and that's where mutability becomes critical. For now, new object, moved name. Variables aren't limited to numbers. A name can be bound to any object, including a type itself. Consider var is set to type or 5 times 4. Python evaluates inside out. 5 times 4 produces 20, a new int object. Then the type function asks, what kind of object is 20? The answer is int. So var is bound to int. The type itself is now the object stored in memory under that name. Types are objects too. This is why Python feels uniform. Numbers, results of expressions, even types all follow the same rule. Everything is an object, and any name can point to any of them. 3 rules summarize Python's model. Every value is a typed object, and the type defines valid operations. Assignment binds a name to an object. Evaluate the right side first. Create a new object, attach the name. And the name can hold anything, even a type. With this mental model, every line of Python reads the same way. Build objects, name them, combine them. Next, we apply these same rules to a new kind of object, the string.